protected. Chung. Before I talk about my research, let me advertise the special issue called from the transactions on robotics. It's actually the first special issue in the area of robotics from the approach by transactions on robotics. So we are excited about it. And the deadline for submission is 31st of May. So there's a presence from the DG. So this is a microbox, and our vision is to create something like this in space or in the air. And then there are a lot of interesting control problems we'll have to solve. So I'm not going to talk much about this. It's going to appear as a regular article in Transactions on Robotics. So instead of controlling the individual agent, it's actually to make an analogy to fluid mechanics. It's actually a Lagrangian approach. So it's actually my former PhD student now research at JPR as a partial work. So you can create a Markov chain that can prescribe the transition probability between bin to bin. So basically you can solve the simultaneous stochastic target assignment, so we can figure it to this desired shape. And this is a simulation using 1 million agents to build and construct the Taj Mahal. And then we can actually run the low-level guidance to run this bin-to-bin transition motion planning, and so that we can maybe significantly reduce the computational time for this kind of a large-scale swarm reconfiguration and optimal control. But if you go back to the Lagrangian approach, we can still do our best to improve our numerical efficiency and so on. So this is a small spacecraft, and why it's so difficult? Because you have a large number of agents. So before we actually were inspired by this microbus by Disney, actually we were working on this FemtoSat, swarms of FemtoSat. So the swarm here means that it should be at least hundreds or thousands of spacecraft, and it's not practical to build and launch thousands of CubeSat, even CubeSats. So we were actually designing this microbot or FemtoSat for spacecraft. It's a 100-gram spacecraft. It has a full system of functionality. It has reaction gears and all these computers and thrusters. So is it possible to really build a 100-gram class satellite? The answer is yes, because we built a 93-gram batbot. So this is a batbot that can fly like a bat. But obviously I was joking. This is a real bat. The video from our collaborator, actually Sharon Swartz and Ken Wood, they are the best people in terms of characterizing the aerodynamics and these fluid motions of bat. And if you actually understand the nonlinear control theory, previously the best model for flapping flight was hummingbird or insect flight. And for insect flight or hummingbirds, the aerodynamics are more complicated because the aerodynamics are unsteady. But for this kind of bat or bird scale airplanes, the aerodynamics are less unsteady. However, it's a grand challenge control problem because you have basically 40 joints on the wings, and then you add this complexity or flexibility of the partial differential equation based structural dynamics. Then it's a grand challenge control problem. So we went ahead and based on our prior work, and we wanted to build our batbot. Recently, it was published in Science Robotics. And then this is a work by my postdoc, Ali Reja, and also my colleague at Hutchinson in Illinois. And it's a lot of hardware work, and eventually it has a full 5 motors, and each motor has encoder feedback, and it has a very powerful microprocessor. We are running some optimization-based algorithm, so we can actually run sophisticated control algorithm here. So it's an interesting machine, and then in order to kind of enable this kind of a machine, we are really tapping into some advances in nonlinear control theory and optimal control. So this is another project funded by the NSF, and we are looking at building a robotic tycoon that can fly like a tycoon, so eventually they can herd real birds flocking around the airfield to solve the bird strike problem. And this is the related work showing some bird like an airplane perching. So how can you solve this kind of flocking or like a swarms of spacecraft or microbots reconfiguring into a very complex shape in real time? It's obviously an optimal control problem. So you have to minimize a certain cost function. And then you have a dynamics, and oftentimes the dynamics are nonlinear. and then you have to avoid collision, and then there are various constraints, including some control input constraint and so on. But typically in optimal control problem, you have to define the initial condition and the terminal condition for each agent. For this kind of problem though, if you define that, you are maybe defining the terminal condition for initial condition, very suboptimal or very less optimal manner. So what you can do is that you have to actually solve the optimal control of generating the collision-free optimal trajectory connecting initial point to the target point. At the same time, you have to solve the target assignment so that you can drive these swarms of millions of agents into the target shape. So that's the target assignment problem, and then we are basically presenting the how can you solve this target assignment problem with the optimal controller in a kind of very computationally efficient manner, doing some multiple simplifications, including complexification of a collision avoidance constraint. And obviously that's very conservative. I'm going to just briefly talk about how we're going to relax that. But so there are a lot of hidden information here, so we kind of present many multiple conditions that can ensure this resolvability and feasibility of this sequential complex programming problem that can actually, so sequential part is there to somehow improve this hyperplane-based complexification of collision avoidance constraint. And then at the same time, we are solving this target assignment problem simultaneously so that you can actually drive this agent into the particular shape. So some experimental visualization hardwares, and then this is actually visuals using the actual 3D spacecraft dynamics that are configuring into the UI shape, so that we can actually determine the target location individually in optimal fashion in real time. So the one problem is that if you actually exploring in the environment, by doing this hyperplane approximation of collision avoidance, it's going to be very conservative. So what you can do is that you can expand the sphere that can define your collision-free convex regions, and then the outcome is recent work by Stochastic, and then also we have Chung here. How can you ensure the robustness? Basically, when you actually solve the optimal control problem, you have to define the uncertainty bound. By the way, optimal control is always optimal, again, with respect to the dynamic model you have, or the state information, but such information is always inaccurate, right? So then we can kind of bring in this nonlinear control theory. So my prior work basically looked into this synchronization of nonlinear dynamics on a graph, but typically for aircraft or spacecraft or even robots, you don't want to bring this spacecraft or robots into a common trajectory, because it means that they are going to collide, and then you don't really predict the consensus synchronized trajectory. So what you can do is that you can do this time scale separation so that you can drive these swarms of lobos into a certain synchronous behaviors, and then you can try to control that synchronized trajectory. So very briefly, I probably have a few minutes now. And instead of using the reapproach-based method, this is kind of a new technique for the contraction theory. So basically, you look at the incremental stability of the trajectory. So the basic idea is that instead of looking at the scalar function that's actually decaying over time, that's the reapproach function, given the dynamics, you look at how these multiple trajectories actually converge into a single trajectory. So that's actually contracting, which means that from any initial conditions, this solution or trajectory of your dynamics is converging to a single trajectory. And how can you mathematically quantify that? That's math right there. So you can quantify the contraction. And so that's the theory I've been using for a number of years. But a basic idea is that once you prove the exponential stability of this trajectory of your dynamics, then once you have a disturbance, and as long as the disturbance is bounded, or even in a known sense, then you can actually prove the bounded output. So it's bounded into bounded output stability or finite gain empty stability. So then that's going to be very useful for robustness analysis for tracking control, as well as you actually use that bound, predicted the error, and you feed back into the optimal control problem. So I don't think we have time for this. One example of this using nonlinear control and synchronization is actually nonlinear observer. So when you go to the robotics conference, oftentimes we have a very good filter-based algorithm, but oftentimes they are using the extended Kalman filter. But if you have used extended Kalman filter, it's very easy to see that if you don't initialize your covariance matrix, if you don't find the correct gains or covariance matrices for noise and processing noise, then oftentimes they diverge because dynamics are nonlinear. So oftentimes, the SLAM algorithm is not mobile robot anymore because we are maybe looking at now these days aerial robot or spacecraft or six-stop robot. Then the dynamics that's carrying the camera is nonlinear. Furthermore, you're using vision-based method, then oftentimes there's additional layer of dynamics that are highly nonlinear. So for that kind of problem, we can actually extend this kind of a synchronization or nonlinear stability tool for to nonlinear stochastic dynamics. So imagine that you have a stack of two dynamics here, A and B, and then if the dynamics is a stochastic differential equation without noise. And then if original dynamics without noise contracting or exponentially stabilizing, you can actually go ahead and prove that is, in essence, the noisy version of those trajectory A and B are kind of contracting, but that the distance between these two, A and B, will not be zero, but it's going to be bounded. So we can kind of prove that with a little bit complicated math. So using the so this is basic synchronization, right? Synchronizing trajectory A and B. But one application of that is observer. So as I said earlier, this simultaneous localization mapping problem is a very interesting estimation problem, especially with the vision, because you can define your measurement equation as you like. And oftentimes, that's the nonlinear function of your state. And also, as I said earlier, you have nonlinear dynamics. So we can propose to actually apply that nonlinear synchronization or nonlinear to the observer, where you can actually try to estimate between x and x hat. So instead of driving the A and B trajectories into single trajectory, for the control problem, here you are trying to drive your estimated trajectory x into your true trajectory x. So you can apply that, and eventually what you can do is that you formulate this convex optimization problem to solve this nonlinear filtering problem, and everything is a convex, and the cost function is actually the convexified version of that nonlinear, the mean squared error term that you analytically compute it. And obviously, it's very easy to show that it can easily outperform the extended Kalman filter. So my point is that by combining this nonlinear control theory and optimal control theory and some of the robotics tools, we can actually make some good advances here in terms of guaranteeing some robustness and optimality together. Thank you so much.